Hi, I'm Dr. Jessica Cherry.
And I'm Forrest Kirst, a commercial pilot.
And today we're going to talk about an experiment we're doing using a small aircraft where we've mounted a sensor package to the aircraft to measure temperature, humidity, and pressure, as well as elevation and longitude and latitude of the airplane. And with the package, we're going to sample the local winter inversion here in Fairbanks, Alaska. And an inversion is where you have the surface atmosphere that's closest to the land is colder than the atmosphere above it, which is the opposite of normal conditions throughout the year throughout North America. Forrest, maybe you could tell us more about how a pilot experiences an inversion during the wintertime.
On the ground during our pre-flight, it's very cold out this morning. It's minus 28 centigrade, which is about minus 30 degrees Fahrenheit. So doing our pre-flight, it's extremely cold, hard on the airplane, hard on the people. For flying at the colder temperatures for doing these experiments, we're somewhere between minus 20 and minus 40 degrees. So we have to dress for that temperature inside the airplane as well as when we're outside of the airplane. When we're doing our pre-flight, we have to be extremely careful not to damage the plastic parts on the outside of the airplane. Extremely careful not to touch the metal parts with our fingers because we'll get contact frostbite. And we have to be real careful just with everything because it's just so cold. We have to dress as if we're going to be outdoors the whole time, and we use the aircraft heater to make it comfortable in our clothes and so we can see out the window. When we get the airplane running and we do our takeoff roll, we have increased engine performance and increased lift because of the colder, denser air. So we get off the ground earlier and have a better climb rate. When we reach the inversion layer, quite often the windows will fog up. The airplane's performance will decrease slightly because it's warmer air, produces less lift, and it produces less power from the engine.
When an inversion is present, air doesn't move anywhere, especially it doesn't want to move up. And so the classic look there is the steam out of the power plant or automobile exhaust, any kind of wood smoke or such, will come out of a chimney and then just flatten out and not move up. And if it moves horizontally at all, it's very slow, just creeping along. When you see that kind of lack of air movement, especially when there's clear skies, the sun is maybe low on the horizon, that is an inversion day in interior Alaska.
The reason it is so cool in the far north during winter is that the incoming radiation is at such a low angle. Now, as the atmosphere begins to cool in late fall, we start to get snowfall, which causes the land surface to be white, and light colors reflect incoming radiation right back, which causes additional cooling. And it's the reason we have a persistent inversion from late fall through early spring here in Fairbanks.
To get a radiation inversion to form, you need clear or mostly clear skies. You need no wind or very little wind down at the surface. And you need to have the sun under the horizon or high noon in December such that even if the sun is up, it's so low it doesn't really feed in any energy. When those three things happen, you lose heat to space from the surface of the Earth, but you're not getting any new heat in, and you get a very cold layer of air hugging the ground, cold, dense air that just lays down in the bottom of the valley. That's the classic radiation inversion setup.
So as we do our experiment with the aircraft, we're going to use a similar instrumentation package as is mounted on the standard weather balloons. We're going to measure temperature profiles, relative humidity, and pressure. And we're also going to tie the sensor package into a GPS unit, a global positioning system unit, so we know where the aircraft is located relative to the topography. So now I want to tell you about the instrument package that we're using on the aircraft. First of all, we use a NiCad 12-volt battery to power the data logger and the instruments. The data logger records the output from the meteorological sensors, which here include a temperature and relative humidity sensor, and a pressure transmitter, which works like a barometer to measure atmospheric pressure. This particular one is going to plug into the static port in the aircraft, which also helps power some of the aircraft instruments. Finally, we have the Global Positioning System computer, which measures the latitude, longitude, and altitude of the aircraft. This one has an accuracy of about 10 meters, which is perfectly fine for what we're trying to do here. Here's a picture of our temperature and relative humidity sensor installed on the aircraft. So this is an FAA approved plate here mounted to the window. And we want the temperature sensor mounted towards the aft of the aircraft so we don't get air rushing in and it has a chance to equilibrate to the environmental conditions. And then finally, our pressure sensor is connected to this static port in the airplane, which again just measures the ambient pressure of the atmosphere where it hits this little hole in the plane. That's piped back into our pressure sensor inside. So one of the things that we're going to go out and do today is that we're going to attach the sensor package to the aircraft, and then Forrest is going to take off from Fairbanks International.
To get repeatability for the data, we flew in and out of Fairbanks International, Nenana Airport, Ladd Army Airfield, and Eielson Airfield. So we do a very slow climb up through the inversion layer, climbing at about 100 feet per minute. Just very slow climb to the top of the inversion, find out where the ceiling is, and then once we're at the ceiling of the inversion, we do very slow porpoising up and down through the inversion to see if it's stable, if it's got different characteristics throughout it. Then we get to the next airport and we do a very slow descent into the airport at about 100 feet per minute, all the way to the ground.
Weather balloons here at Fairbanks International Airport are released by the Weather Service twice a day, and the timing of those releases are such that they are coordinated with all the other releases around the world. And that data then, which provides a vertical profile of temperature and relative humidity and pressure in the atmosphere, is then integrated into the forecast models run by the Weather Service.
How can you forecast the temperatures when an inversion is present? It is a difficult puzzle. In Fairbanks, often the weather forecast says today, clear skies, high temperatures from 20 below to 10 above, coldest in the valley and mildest in the hills. A 30-degree range. This is not uncommon in the interior winter. It's a difficult puzzle to try to put very precise numbers. We need a broad range because within that shallow layer, you go from such cold temperatures to such warm temperatures. That's just the way it is here in the inhabited elevations of interior Alaska. Well, anything you want to forecast, including a temperature inversion, has to be studied. You have to learn how the inversion works in order to forecast its future behavior. And part of learning how it works involves gathering data. And every day out at the Fairbanks International Airport, a weather balloon is launched. On the end of the balloon is a thermometer, up it goes, and we get the vertical profile of temperature in the atmosphere. And that's real good data. You can see the inversion with that. Problem is, the weather balloon only goes up twice a day. And for forecasting, detecting and forecasting the jet stream, which operates on broad spatial and temporal scales, twice a day is for most purposes adequate. However, down here in this fine spatial scale right in urban Fairbanks, we need more than twice a day to really understand the inversion, especially its formation and its dissipation.
So the weather balloons that are released at Fairbanks International are timed with all those other global releases, and they are not actually at times which are very dynamically active here in Fairbanks, which is another reason that we're interested in doing this experiment with an aircraft and also additional weather balloon releases to sample some of those more dynamically active times of the day.
Basically, in preparing the sondes, you have to take the sonde out of the package, prepare the sensors, and then you'll fill up the weather balloon, then need to calibrate the instrument inside. So that's the most important part of balloon preparation. So when we're calibrating the instrument, we make sure that the temperature of the sensor is realistic with the temperature either of the room or outside, wherever the sonde is being calibrated, as well as pressure, making sure that's at our level, and also the relative humidity, that looks realistic. We use these weather balloons that when they're filled up with helium, they're approximately 6 feet wide, And by the time that they reach the top of the atmosphere where the balloon pops, they're about 20 feet wide. So they're huge. It's hard to even imagine. After we get clearance from the FAA, we'll go outside, take the radiosonde, attach it to the balloon, and then make sure there aren't any planes going by just in case, and let her go. And the computer inside actually picks up the signal automatically. It'll tell you exactly when the balloon was launched, and the data will come processing in from there. After we launch the balloon, I'll go back inside the building and to make sure that the data that's coming in on the computer looks realistic, making sure the pressure decreases with height, the relative humidities look realistic, and in my cases, looking at temperature inversion, that the temperature is increasing with height. Typically in the atmosphere, we see temperature decreasing with height, but in these special cases, that's what I'm looking for. And then I can watch as the temperature progresses vertically into the atmosphere, as that sensor's rising, and I can see where the top of the inversion layer is. So the National Weather Service currently launches weather balloons twice a day, but I wanted to launch weather balloons more frequently than that to see what was happening between those launches. So I wanted to take a look at what's happening between that 4 p.m. launch and that 4 a.m. launch, and then what's happening between the 4 a.m. and the 4 p.m. So I launched these weather balloons every 2 to 3 hours to gain a better temporal resolution of what's going on in the atmosphere.
Our research asked the question, what will surface-based temperature inversions look like in Alaska over the next 100 years? And the primary tool for studying future projections are global climate models. In fact, they're the only tool. But they're not perfect for answering our question because we're interested in information over a city landscape scale, which is a few miles, 5 miles, 10 miles. Global climate models provide information on a 100-mile scale. So we need to get that information from this coarse scale and downscale it to a higher resolution so it's useful for us. And the way we do that is we take climate information from the global climate model and we feed it into our regional model, which has a domain over Alaska at a resolution of, say, a few miles instead of hundreds of miles. And the large-scale climate comes from these global climate models, and then we run our simulation over Alaska. We have done regional downscaling simulations for 20 years in the 20th century, from 1979 to 1999. We've done 10 years from 2010 to 2019, and then from 2050 to 2059, and 2090 to 2099. So with the regional model, we've taken these 4 slices over time, fed by the global climate model. And what we find, first of all, in the 20th century simulation is that the regional model does a much better job of simulating the vertical surface-based temperature inversions over Fairbanks and the other cities in Alaska. And as we go through the 21st century, those 3 other slices, as the global climate warms, we find that the temperature inversions in the lowest layer don't really change in strength. The strength stays the same, but the whole profile gets warmer. So this study provides a first look at what would be happening to temperature inversions in the future. We need to ask other questions like, how will this frequency change? Will they occur as often? Will the season be much shorter? There's a variety of other questions we need to ask to develop a better picture for how temperature inversions will change in the future. And our first cut answer that we have suggests that we'll still have to worry about the same sort of air quality issues because in the near surface, the strength of the inversion will be about the same.